Today we are going to solve the question 23. In question 23, it is asked, consider a three-dimensional Kate space if a certain Kate of orthonormal Kates, say 1, 2 and 3, are used as the base Kates. The operator A and B are represented by in this form and in this form with A and B both real. Question A, obviously A exhibits a degenerate spectrum. Does B also exhibits a degenerate spectrum? We have to check this, and in question B we have to show that A and B commute, and C, we find a new set of orthonormal Kates with which are simultaneous eigenkates of both A and B. Specify the eigenvalue of A and B for each three eigenkates. Does your specification of eigenvalues completely characterize each eigenkate? So let us check. First say assume that 1 is equal to, let us take the 1 in column matrix form is 1 is represented by 1 0 0 and 2 is represented in column matrix form as 0 1 0 and 3 is represented by 0 0 1. So this for A operator the eigenvalue corresponding to this eigenkate is A 1 0 0, which will be A 1 0 0, and the eigenvalue corresponding to 2, that means A 0 0 0 minus A 0 0 0 minus A 0 1 0, it will be minus A 0 1 0, and A3, similarly A3 will be same as A2, which will be minus A 0 0 1. That means the operator is degenerate because this operator has same eigenvalue minus A corresponding to eigenkates, which is 2 and 3. Now let us check whether B is B also degenerate or not. So let us calculate first the eigenvalues of the B matrix. B is represented by B 0 0 0 0 minus IB 0 IB 0. Now if lambda is its eigenvalues, then it will be satisfied B minus identity into lambda, its determinant should be 0. So let us calculate this. That means B minus lambda 0 0 0 minus lambda 0 0 minus IB minus lambda, this will be plus IB, this will be minus IB, is equal to 0. That means B minus its determinant will be 0. It means B minus lambda into lambda square minus B square is equal to 0. That means the values of lambda is lambda 1 is equal to B. This is the first eigenvalue. The second eigenvalue is lambda 2 is equal to plus B, and the third eigenvalue lambda 3 is equal to minus So from here we can see that this operator is also degenerate in degenerate because its two eigenvalues are same. One of its So these two eigenvalues are same. So that means let us check what it is eigenkets are. First eigenkets will be same as A, which will be 1 0 0, and the second eigenkete will be, let us calculate that. This eigenvalue is corresponding to this eigenkete is corresponding to this eigenvalue. Now let us check the second eigenkete. Suppose the second eigenkete is x, y, z, will be b x, y, z. That means v 0 0 0 0 minus ib 0 plus ib 0 into x, y, z is equal to bx, by, bz. That means px minus ibz plus iby is equal to px, py, pz. From these two equations we can calculate that px is equal to bx, which is trivial, which is true, which is trivial, and from other two elements, that means minus ibz equal to by and iby is equal to bz. That means from here we can calculate that z equal to iy, and from here also we can see that z equal to I. So let us put y equal to 1. So that means the one eigenkete will be 0. Suppose bx equal to, then it is true for any value of x. That means we can put x equal to 0 0, and let put y equal to 1. That means y equal to 1 and z equal to y. So it is one eigenkete corresponding to the eigenvalue plus b. So this eigenkete and this 0 1 0 0, these two eigenketes have the same eigenvalue same eigenvalue that means, and since these two eigenketes are linearly independent, that means we cannot express these eigenketes in terms of the eigenketes of 1 0 0. That means these two are linearly independent eigenketes have the same eigenvalue plus b. That means this b also degenerate. Now let us check the third eigenketes. So third eigenkete will be bx minus I bz and iby. Third eigenkete will follow this relation. Third eigenkete will correspond to minus b, so that means it will be minus bx minus by minus bz. That means bx will equal to minus bx, that means x equal to 0, and from these two we'll get ibz equal to minus by. From here we'll get z equal to minus iy. and from third equation also we will get z equal to minus iy. So if we put y equal to 1, that means the eigengate will be 0, 1 minus I. So this eigengate is corresponding to the eigenvalue minus b. Again, so here the three eigengates with the operator b are, one is 1 0 0 corresponding to the eigenvalue b, another is 0 1 I which corresponding again to eigenvalue b, and third is 0 1 minus I which corresponding to the eigenvalue minus b. And here the b is twofold degenerate, means here the two linearly independent eigengates have the same eigenvalue b. Now let us check whether the commutation relation between a and a comma b, which means we have to calculate ab minus ba. So first let us calculate a times b, which is a 0 0 0 minus a 0 0 0 minus a multiply b 0 0 0 minus 0 0 minus ib and 0 ib 0. That will be ab first term, second term will be 0, third term will also be 0, so 0 0. This will be 0, this will be this again from here, this multiply by this will give 0, this multiply by this will again give 0, this multiply by this will give plus I AB, and last let us check the third element, that this multiply by this will give 0, this multiply by this will give minus IAB, this multiply by this will give 0. That means this matrix is actually AB times 1 0 0 0 0 1 and 0 minus 1 0. Now let us check what is the value of b into a. Now ba will be v 0 0 0 0 ib 0 minus ib 0 times a 0 0 0 minus a 0 and 0 0 minus a. So what it will be? Let's first multiply this time this will give ab, second it will give 0, third it will give 0. Now this time this will give 0, this time this again will give 0, this time this will give plus this, there I, there is minus I, so this will give plus I A B, and here this and multiply by this will give 0, this multiply by this give minus I A B, this multiply by this row will give 0. That means we get AB into 1 0 0 0 0 I 0 minus I 0. That means this matrix and this matrix are same. So that means AB is equal to BA, that will be A minus BA is equal to 0. That means A and B commutes. A comma B commutes. So we have proved the equation question number B. Now let us check. See, for a new set of orthonormal kets which are simultaneous eigenkets both A and B, specify the eigenvalue of A and B for each of the three eigenkets. Thus, your specification of the eigenvalues completely characterize each eigencase. Now, let us check what is whether the eigenkets of operator B is also eigenkets of operator A. So let us check that. If we will check it, we will get the answer of C. So A operate on first eigencase corresponding to what? Three eigenkets 1 0 0. So let us 1 0 0, and we know that this eigenvalue corresponding to will be B 1 0 0. So that means this is the eigenkets of A also. Now check this 0 1 I, which is again eigenkets of B corresponding to plus B. Let us check. This means A 1 1, this means 1 into 0 1 0 plus I into 0 0 1, which is nothing but A 2 plus I 3. Now after going through this step, let us normalize these eigenkets of the B. So if we normalized eigenkets will be, if we normalize, that means we have to divide this by every element square. That means 1 square plus mod I square means 1 square, that means 1 by root 2. So we have to, the normalized eigenkets will be 1 by root 2 into this, so there will be 1 by root 2. So here also there is 1 by root 2. Again we know that if we operate on this state, since 2 and 3 has the same eigenvalue minus A for the operator A, that means this will be 1 by root 2 minus A 2 minus I A 3. Since 3 and 2 is eigenkets of A with same eigenvalue minus A, that means it will be minus A 1 by root 2 2 plus I 3. That means this is a simultaneous eigenkets of the operator A and B. That means normalized simultaneous eigenkets of A and B will be, one is 1 is 1 0 0, corresponding eigenvalue is A, and another is 1 by root 2 0 1 I, which is actually, this is actually 1 in matrix representation, and this is actually 1 by root 2 plus I 3, and corresponding eigenvalue of the operator A is minus A. Now let us check the another simultaneous eigencase of A and B operator. So that will be 1 by root 2, since normalized factor 1 by root 2, and other eigencase of the operator B with minus eigengates with eigenvalue minus 2 minus minus b, sorry, minus b. Why I am telling it is 2? This is actually minus b, corresponding minus b, sorry. If this is minus b corresponding to eigenvalue minus b, that means that is 1 by root 2 0 1 minus I, which is actually 1 by root 2 1 by, which is 1 by root 2 2 minus I 3. If we operate a on this state, we will get root 2 2 minus I 3. Since these again see a eigengates of the operator a with the same eigenvalue, we will get minus a 2 minus I 3. That means minus a into the same eigengates, that means 2 minus I 3 1 by 2. So these three are these, and these two are the three simultaneous eigengates of the operator a and b, of the operator a and b. Now last, does your specification of eigenvalues completely characterize these eigengates? Now for the first eigengates, the eigenvalue of the operator a and b is a comma b. For the second eigengates, suppose let us assume that there is 1 prime, this is 2 prime, this is 3 prime, which are our new eigengates, simultaneous eigengates. Then the eigenvalue corresponding to the first eigengates will be a comma b. So we can represent the first eigengates as a comma b. Now for the second eigengates, means 2 prime, we can retain as the eigenvalue corresponding to a operator is minus a, and corresponding operator b is plus b. So that means 2 prime can be written as this. This is the eigenvalue corresponding a, and this is the eigenvalue corresponding b. Now the third eigengate, that means this, the eigenvalue corresponding to the operator a is again minus a, but the eigenvalue corresponding to the operator b is minus b. That means we can represent, specify 3 eigengates completely differently. That means now our eigengates can be specified by the eigenvalue of the both operator a comma b. Now first will be a comma b. This is a one eigencase, another is minus a comma b. This is second eigencase, and last eigencase a minus a comma minus b. So that means we can specify 3 eigengates, simultaneous eigengates of the a and b operator by their eigenvalues. So we have done the question 23. Now we will solve the question 24. In question 24, it is asked in question A, prove that 1 by root 2 1 plus I sigma x acting on 2 component spinor can be regarded as the matrix representation of the rotation operator about the x-axis by angle minus pi by 2. So let us check it. So first operate this on an spinor 1 plus I sigma x, that is plus is set. So operate this operator on eigengates of the plus sz. What we will get? We will get 1 by root 2. First will be plus sz, second will be plus I sigma x plus sz. As we know that sigma x sx operating on plus sz will give h cut by 2 minus sz. That means, and sx is actually sigma x into h cut by 2. That means sx operating on plus sz will give minus sz. That means it will give 1 by root 2 plus sz plus I minus sz. And from the question 9 we know that these eigengates is nothing but the eigengates of a operator sigma dot n cap, where this n cap, this means n cap is here, this unit vector n cap make a angle beta with the z axis, and its component on xy plane makes an angle alpha. So let us check what is the alpha and beta here. Here cos beta by 2 is equal to 1 by root 2 and sine beta by 2 is equal to 1 by root 2. Here the eigengates of the sigma dot n from the question 9 we know that will be cos beta by 2 plus sz plus e to the power I alpha sine beta by 2 minus sz. So that means beta by 2 equal to pi by 4, since 1 by root 2 means cos pi by 4 and sine similarly same. That means beta equal to pi by 2 and e to the power I alpha is equal to I. That means alpha is equal to pi by 2, since e to the power I pi by 2 is alpha I pi by 2. That means it actually a state that is pi by 2 and alpha. That means this state is corresponding to plus sy. How I know that? Because here the beta, here let me use another color. Here the beta is pi by 2 and alpha is also pi by 2. Alpha is also pi by 2. So that means this operator give a rotation of this. Let me use another color. This operator rotate this z, the eigengates of the sz operator, to a rotation to pi by 2, which is in clockwise direction, in this direction, clockwise direction. What is the amount of rotation? Pi by 2. So that means this operator rotate this state around the positive x-axis clockwise pi by 2. That means the first part we have seen that. That means this part, that the matrix represents a rotation operate x-axis by an angle pi by 2. So we have seen that. Now let us see the second part. B. Construct the matrix representation of sz when the eigengates of sy are used as the base gates. In the lecture where we have learned the change of the basis and unitary operator, we have seen that if u a is equal to b, that means operator u, a unitary operator, change the basis a to b in this way, then the any matrix representation in A will change its form to be as follows: U dagger A U. Here the operator U is 1 plus 1 by root 2 1 plus sigma x, that will actually a unitary operator which change the basis plus sz to the basis sy plus sy. So that means here U, let us check U is a unitary or not. U dagger means 1 by root 2 1 minus I sigma x. Its dagger, since sigma x is a Hermitian operator, that means 1 minus I sigma x, that means U dagger U will be 1 by 2 1 minus I sigma x 1 plus I sigma x, which is 1 minus I sigma x plus I sigma x plus sigma x square into 1 by 2. This will be cancelled, and we know that sigma x square means 1. That means 2 by 2 is equal to unitary operator. Similarly, we can prove that U dagger U is equal to 1. That means identity operator. That means this U is a unitary operator. So now let us check what is the form of the sigma z. Sigma z in the z basis will look 1 0 0 minus 1. Now let us check what is its form in the basis of in this basis. So that will be U dagger that will 1 by root 2 1 minus I sigma x sigma z into 1 plus I sigma x into 1 by root 2. That will give 1 by 2 1 minus I sigma x. This will be sigma z plus I sigma z sigma x, and we know from our previous problem number 8, I think problem number 8, that is sigma z into sigma x will be I sigma y. That means half 1 minus I sigma x into sigma z plus I into I sigma y. That means half 1 minus I sigma x into sigma z minus sigma y. That will be half into sigma z minus sigma y into again minus I sigma x sigma z and plus I sigma x sigma y. So here will be plus sign. So that means since sigma x sigma z will be minus I sigma y, that means this will give plus half sigma z and this will be minus, I think something I have missed it will be plus. So I sigma y sigma z into sigma x will be I sigma y. So it is fine. So that means it will be sigma y minus I sigma x sigma z will be sigma x sigma z will be minus I, that means plus I square, that will be sigma minus sigma y, sorry, that is minus sigma x, and this will be plus I into sigma x into sigma y. We know that is equal to I sigma z, that means I into sigma z is equal to minus sigma square, that means 1 by 2 minus sigma y minus sigma y, that will be minus sigma y. In that means it will be 0 minus I 0, and this sigma y actually in represent in sz basis. So in sz basis sigma y will be 0y minus I 0. So that means in sy basis sz will be 0 minus I 0. So we have solved the question B part of the question 24. Now we will solve the question number 25. In question number 25 it is asked, some authors define an operator to be real when every member of its matrix element, that means B dash A B double prime, is real in some representation, a representation B basis. In this concept, representation independent, that is, do the matrix element remain real even if the some basis other than B is used? So check your assertion using familiar operators such as sy and sz. So let us check that. So that means our element aij in matrix representation B will be bi a bj, which is real for all values of I and j. So let me check. So all values of I and j, and then let us express this matrix in another set of eigenkets or basis, that means in basis C. What we'll get, that the matrix L element Lm in C representation of C basis will give, from the orthonormal condition we know that, no, it will be this will be CL a CM. From the orthonormal condition of the B basis we can write it summation of Ij CL Bi A and Bj Cm, that will be summation of I comma j CL Pi A Bj Cm, that will be Ij CL Pi Pj Cm. This will be a Ij in B representation in the P basis. Now these all are reals, but we don't know it is real, whether this is real or not. If it become imaginary, then this element Lm represented in C will also become imaginary. So in general it is not true that if one matrix all element of one operator in matrix representation in one basis is real, then it is not necessary that it will be the all element will remain positive in another basis, which is C. Now for example, sigma z in the z basis it will be 1 0 0 minus 1. Here the all elements are real, but the sigma z in the y basis will, as we have checked in the previous problem number 24, it is 0 minus y I 0, which is actually its elements are imaginary. So we have solved the question number 25.